Good afternoon, ladies and gentlemen. Great to see you all here. What a beautiful venue this is. My name's Kirsty Gogan. I'm the co-founder of TerraPraxis, and it's my absolute honor to be moderating this panel discussion today with such a distinguished group. So we have Eric Ingersoll here from TerraPraxis, also my co-founder at TerraPraxis. We have Maggie Manley from Arc Clean Energy. Great to have you here. Thank you so much for joining us. And Andy Hayward from Brunswick New Power. So I'll just kick off by saying that, you know, oh yeah, good. There's the kind of opening slide. We're going to start with kind of a complicated chart for you all today. So really the purpose of this discussion is to kind of try to begin getting our heads around the idea that, you know, there is like hundreds of gigawatts scale of demand for heat and power and hydrogen in the oil and gas sector, upstream, downstream, that needs to be decarbonized. And, you know, one of the ways in which we could be delivering those heat and power and hydrogen services is through advanced nuclear technologies. And we think that they have a huge amount of potential because of their high capacity factors and their high power density, and the fact that, of course, that they also make heat and power potentially in a very cost competitive way. The problem is that the oil and gas sector doesn't necessarily want to be an owner or operator of those technologies, and so it's a pretty tough product to sell. So what we have here is a sort of a picture of what is essentially the kind of value chain from the supply chain for those components and materials through to the sort of manufacturing and assembly and construction and operation to the customers ultimately for those products that we're describing. So we tried to sort of put this panel together to try to represent somehow that value chain. And then, you know, I'd like to encourage each of you to sort of, you know, represent that position and think about, you know, how you're going to be supplying into that market and how you'll be interacting with each other across that value chain. So that's how I'd like to sort of set up this discussion. And I'm really excited to hear from each of our speakers. I'll invite each speaker to make some opening remarks for, you know, several minutes each, and then we'll go into the discussion, and I'd really love it to be quite interactive. So if you have questions, you know, please do raise your hands, and we'll be taking questions from you guys too. Okay, so Eric, over to you.
Thanks, Kirsty. So we had a sort of a second slide that showed that there are in addition to the sort of people exchanging goods and cash and services with each other, there are also some other people that need to be part of the picture. And what I'd really like to talk about today is how we create an entirely new industrial ecosystem to meet this very large demand for heat and power and hydrogen. And we really, what we have today in the way we use nuclear power is kind of large power projects that are delivered through a complex, slow design each project separately, and then do a very long, expensive, complicated build process. That's not what we're talking about. So I think this is really kind of a conceptual exercise to take the requirements that we have from these large customers, both in terms of scale and in terms of when they need these products, when they need the heat, when they need the hydrogen, and when they need the electricity in order to decarbonize, and also the scale that they need that delivered at. And to begin to sort of think through how we might actually accomplish that, and what kind of business models we would need, and what kind of physical models, and what would that new industrial ecosystem look like. So that's called the Gigafactory, which Kirsty mentioned in her talk. Here's a kind of a plan view of it, and you can see that there's some manufacturing buildings over on the left where things are being put together, and then there's a field where reactors are being installed and then operated, and that's where power is being made. And then there's electrolysis and other downstream activities using the power and the hydrogen to make downstream products. So here's kind of the diagram version of that. And again, this is answering the question of how do we do this at the 100 gigawatt scale. As Kirsty mentioned in her talk earlier, a 200,000 barrel a day refinery, which is not very big, is around 20 to 25 gigawatts. So, you know, there's no power plant in the world that is that big. So this is what we're talking about when we say we need kind of to redesign the system for this kind of scale. And I think we've seen in other sectors, such as for batteries and cars, that having a standardized manufacturing process like Tesla has, that you can then go and just kind of roll out these factories, is a way to achieve scale and reduction in cost of the order of what we need to accomplish in this sector. And what you see here is that there's these things then become the enabling source of energy for the downstream products that oil and gas companies are making today, fuels and chemicals and ammonia. So I'm not going to go into all the detail on the slide, but the main thing that we're doing here is transitioning from this sort of project-based approach, which is very expensive and is not designed for scale, to what we call the product-based approach, where you're really designing every part of that system for high-volume manufacturing and for low cost. And that kind of cost is really transformative. So the studies that we've done, which have been reviewed by the Electric Power Research Institute and various oil and gas companies, have really indicate that you can reach large-scale production for around $1 a kilogram or $1,000 a ton for zero-carbon hydrogen. And when you do that, that means that you can make ammonia at about half of today's cost. So half of the cost of making ammonia today with zero emissions. That's a very large market. The ammonia market's currently about 170 million tons a year. But it will get a lot bigger as ammonia is used as a way to transport hydrogen globally and as it's used as a fuel in power plants. So here are just some examples. We think the power generation part of these plants can be built for less than $1,500 a kilowatt, which for a base load generator is a very low cost. And then this gives you some of the targets that you need to reach in terms of the electrolysis cost and O&M costs and so forth, in case there are any people that, you know, like to know what the numbers are in the audience. So that's just a very brief vision of how we might kind of reorganize and create a new industry based around advanced nuclear power plants. And we're very pleased to have some people that are working on bringing some of those to market with us today.
Yeah, that's great. Thank you so much. We've sort of had a good idea now, okay, what's the scale of the demand, so how are we going to bring these SMRs to market?
Right, okay. Hi, Maggie Manley. I'm the fuel systems engineer with ARC Clean Technology. A little bit of background, the ARC 100 is a sodium-cooled fast reactor, uses metallic fuel, 100 megawatt electric, 286 megawatts thermal. You know, it's well suited to industrial applications. It's got safe, reliable, non-emitting source of heat and power. We have partnered with New Brunswick Power, represented here with Andy. ARC's been around since around 2006. I came to Canada and set up shop around 2017 and established a memorandum of understanding with the utility, and we look forward to deploying our first-of-a-kind unit at that site by the end of this decade.
Cool, you're giving me lots of time. So I get to digress a little bit. So in the spirit of this conference, when we're talking about open-mindedness and change and disruption, this is a nuclear crowd talking to oil and gas. So keep the open mind, right? It's the poorest province in the country, New Brunswick, talking to the wealthiest province in the country in Alberta. Okay? So just keep an open mind, all right? The three big drivers that we hear about, we've heard about it today a lot: climate change, energy security, cost. Okay? They're global drivers, right? And each country has to digest them and figure out what they're going to do about them. And we end up with federal policies and practices and regulations which have to get implemented by regions or provinces. So sometimes that's not an easy equation to solve. New Brunswick, I look after advanced reactor development for NB Power. New Brunswick Power is an electric utility that's Crown owned. We're still a regulated province. And we chose to stay that way because almost everybody in New Brunswick heats with electricity. The demand for power is 3 times more in the winter than it is in the summer. And if you try to do that in an open market, it would be really tricky. Okay. So NB Power looked at a long-range plan, tried to figure out how we're going to solve this equation: climate change, energy security, regional energy security, and cost. Because poorest province in the country doesn't want to dump all the cost on the ratepayers in New Brunswick. Right? We want to spread it across the country. So if we're going to do that, we need a solution for the country. Okay? And we're still about half of our generation. We chose to become a nuclear province a long time ago. So there's 2 provinces in the country that operate nuclear operations: Ontario and New Brunswick. It's an Ontario-based economy. And little old New Brunswick's been chugging away with a very efficient nuclear plant since 1983. So we're a nuclear province, and we've diversified our energy mix, our electricity mix at least, on purpose. So we've, about half of our capacity is fossil fuels. And although I heard in the previous session we were talking about an evolution and not a revolution, but I think if you're operating a coal plant, you're feeling like it's a revolution. So, you know, oil and gas, yeah, evolution. We're always going to need oil and gas. And I'm promoting nuclear. You got to keep it. There's a balance to the mix here. But to address those 3 big drivers, MIT, the European Union, all the technical geeks that I've seen produce studies, nuclear's got to be a part of it, right? Somewhere in the order of 15 or 20% of the energy in the world is going to have to come from nuclear. And if you do that, we need to build a lot of nuclear, right? We've always built this centralized, take advantage of economy of scale, build as big a plant as you can, and decentralize the support for it. Well, we're going to flip it. These small modular reactors are going to decentralize the plants and centralize the support. So as NB Power evaluated the options, we looked at about 100 different new nuclear technologies, and through all of our downsizing selection criteria, pretty rigorous process, we picked ARC. It's a liquid sodium reactor. Maggie talked a little bit about it. One of the things that she didn't mention, it has a 30-year operating pedigree at a Department of Energy national lab in the US, right? It operated at a high capacity factor. It was run by scientists who were given the freedom to do some testing that was quite incredible by today's standards. Like they stopped controlling it to see what would happen, and it shut itself down, right? So as we evaluated our new nuclear thought process, we wanted to address the 2 big things that people really are concerned about: a massive disaster or a meltdown, and radioactive waste. And when you guys think about nuclear, that's probably the first 2 things that come to your mind. Well, this generation of nuclear, ARC, which I just described to you, if you leave it alone, it shuts itself down. How do you melt that down? It's self-regulating, right? So we addressed that one. It can also recycle its own waste, and the efficiency of use of the uranium, which is in plentiful supply, by the way, is better So we end up with less waste between the recycling and the more efficient use. So we address the two big issues, right? Meltdowns and waste. That's the drivers for us selecting the technology. It's technology readiness level. The size was really important to us because when we looked around as an electricity company at what are we going to need this energy for, 3/4 of the demand is industrial. If you really want to help decarbonize the world and have the whole rate, taxpayers in Canada pay for New Brunswick's technology development, you got to solve the whole problem, right? So very good for industrial applications and electricity, and any combination of the above. Ramps up and down really quickly, so you can use it for load following and peak shaving and anything else you might want to use it for. So, that's how we're trying to address these drivers. We've partnered with ARC in the development. We're happy to partner with anybody else who'd like to partner with us because we realize we're the poorest and one of the smallest provinces in the country. We've got a great technology. We got some pedigree operating, willing to partner. And that's probably, I'll leave it at that for now. Let some,
Well, that's awesome. And, I think, well, from what you've just been saying, I think everyone's going to want one, So I guess that's the challenge, isn't it? It's like a lot of the technology developers, even despite this incredible 30-year operating pedigree, you still have to build the first one, right? And then how are you designing then to, once you've proven that your technology works, it's operating, then what? Then what happens? How do you how do you meet this demand that Andy's helping you build out there?
Well, we need engagement with stakeholders. We need engagement with industry. We would love to sit down and talk to anybody who wants to talk about what they need for their industrial needs, how can we supply heat and power for industrial purposes. It's not a new technology. The first nuclear pile that was built in 1951 was liquid sodium with metal fuel in it. So there's 70 years, really, of lessons learned using liquid sodium, metal fuel. We recently finished a project with our Canadian nuclear laboratories. They reviewed our fuel qualification plan, and they did not find any impediment to installing our fuel in a commercial demonstration unit. So we're not doing any R&D on our fuel. We're ready to go, and we would like to engage and move forward. We want industrial partners to get involved in the regulatory process, which is it's a slow-moving process. It needs to be sped up, especially for as we deploy nth-of-a-kind units. But we really need industry engagement, and we need to talk to the people who need our heat and our power to meet their non-emitting needs.
Yeah, well, so Andy, I just want to hear from you about the kinds of requirements that you need met, that you're saying, you're describing the majority of the demand is from the industrial sector. What are those requirements for the size of the demand, the kind of costs that need to be met?
Yeah, so first, as an electricity company, we need a 24/7 available source of electricity. So that's in the electricity sector, that's the need. Nuclear fits the bill. We need the cost to be, we don't want to burden the ratepayers in any of the jurisdictions with the cost. And then when you start looking at, most of the cost of a nuclear plant is people. The fuel doesn't cost much. So because of that, you want to run it all the time. And if you have a demand that changes and sometimes goes away, if you're putting steam in the ground to extract oil sometimes, and sometimes you don't need the steam, you want to be able to do something else with it, right? And if you're producing electricity with it sometimes, like we are, and you don't need it all the time because our demand changes seasonally significantly and it changes daily significantly, you want to have another use for it. So New Brunswick has 3 deep sea ports with access to Europe. We've been talking to several people about producing hydrogen, for example, and use the energy from the nuclear plants when we don't need it for electricity to produce hydrogen. So there's an industrial customer in New Brunswick. We don't have a lot of intelligence about oil sands applications, but we have been talking to people and are starting to gain understanding. We think it's a pretty good fit for oil sands. There's cement, steel. When you look at all the industrial applications that need non-emitting energy, it fits with just about everything.
Great. Eric?
Well, I thought it would be helpful to just clarify. I think what we've been hearing about this reactor, which is true for a number of the advanced reactors, is that the companies commercializing them are really engaged in product development. They're not actually developing a brand new technology. So they're trying to make something that has been demonstrated and tested and modeled, and multiple versions have been built, and they're trying to take all that experience and then turn that into an attractive product which can be manufactured and deployed into these types of applications. So this isn't kind of like, hey, can we make one of these things work, right? We know very, very well how to make these reactors work, how to make the fuel and all of that. This is really more about, can we create a really attractive product that meets the requirements of the broadest range of customers? So that's why it's plausible that these things will be in the market in the time frame that we're talking about.
Yeah, and actually just building on that a little bit, I'd love to hear from you all about, some of the sort of traditional concerns that, a potential customer may have about, uncertainty around cost and schedule and licensing, and how will developing these technologies into products create opportunities to really change that paradigm and make it easier for customers to buy these products?
How about I take a shot at that? So 4 biggest challenges in the country right now, and this is about nuclear. A couple of them are nuclear specific. You'll probably recognize some of the others. So fuel. The Canadian nuclear design that exists today uses natural uranium. And I need to advertise this too. You talk about energy security. Canada is the 3rd largest reserves of oil in the world. We have the 3rd largest reserves of uranium as well, right? So there's the federal energy security picture if you look at those two. So fuel, the fuel for these advanced reactors uses enriched uranium, just about all of them. And this is not ARC specific, it's the new nuclear uses enriched uranium. We haven't done that in Canada yet. So we need some help federally with all of the way regulations get written, as you probably realize, is often the technology comes first and the regulations come second. So they get kind of prescriptive, and the regulations get written unintentionally for specific technology. Well, these are new now, so we need to figure out how to use a different type of fuel. So that's number one. The radioactive waste is different as well. It's a different technology, produces different waste. Same deal. We need some regulatory certainty around that waste, where the design of radioactive waste disposal in Canada is all centered around one technology. And if we don't facilitate and federally support different types of radioactive waste, that could kill the whole technology development. So there's the first two. Finances, I talked about. Financial support for developing technologies is really important. The U.S. just threw hundreds of billions of dollars at new nuclear, if you're watching the news. Hundreds of billions, as in Bravo B billions. And Canada hasn't yet. We're 10 times smaller. Just give us 10 times less. We're good. So there's some financial incentives other than just money for development. The nuclear industry's never benefited from tax breaks and some of the subsidies that go along with the other green technologies. So there's some financing issues to deal with. And regulatory, which I've already touched on, but some of the regulatory process, it takes 6 years in the impact assessment process for any kind of natural resource project to happen in Canada. And if you're going to deploy the same technology over and over again, it should not take 6 years every time. And so, there's some regulatory support that's needed. So there's a few. I can keep going.
Love that. License ones build many, and many, many other. Maggie?
Right, so regulatory. The Canadian Nuclear Safety Commission, our regulatory body, they have a voluntary review process that we go through to license a new technology. We successfully went through the vendor design review phase 1. We have made 2 major submissions as part of our vendor design review phase 2 this year. So we made a submission February 22nd on a number of focus areas and did another submission in June. We'll be hearing back from those. So we are on schedule, and we are meeting the regulator being completely compliant. So we are trying to get through this as fast and as close on the 6-year schedule as we can. So far, we've had great feedback. What's the other one you mentioned? Regulatory.
They want money, regulations, fuel, and waste.
Yeah, developing the support for a HALO fuel supply chain in Canada. Right, I remember where I was going with this. We do use enriched fuel. The other benefit of ARC technology is that we fuel once every 20 years. So we're only putting in a core, sealing it up for 20 years, and then walk away. And because we've chosen metallic fuel and liquid sodium coolant, the laws of physics dictate that it can't get any hotter. We can't boil our sodium. We have this huge heat sink to accept any decay heat that comes off with the giant pool of metal around the core. EBR2 did demonstrate they shut off all their power supplies with a scaled down version of our ARC technology, and the reactor increased in reactivity and then just shut itself down. And we're at a ceiling where we're around 300 degrees margin to boiling. I'm the technical person at ARC. So if you want to corner me later this evening, and I can tell you 45 minutes about how our fuel works. I've been working with ARC since last fall to qualify the fuel and get through the process so we can deploy the technology as fast as possible. Because it's not new, it's not novel, it's just about having the market tell us that we're good to go. We're cost competitive now with natural gas, including carbon capture and renewables. So all the drivers are in place. So we're ready to go.
It's fantastic. And I'm sure all of these points you're making about, the regulatory compliance and just being so incredibly safe is just going to be music to the ears of the, health and safety people in the oil and gas industry too, right? Eric, did you want to add something here?
Well, I think one of the things that we've done as kind of an experiment, Kirsty, is referred to reactors as advanced heat sources. And we do that for a reason, because when people hear the word nuclear, they have so many associations which are not always relevant to these new reactors. So they have associations about size, complexity. Oh yeah, that's the kind of plant where you have 1,200 people on staff. Or, that's the kind of plant that takes 12 years to build. Or, that's the kind of plant that can't operate flexibly, right? So we have all these kind of assumptions that they're sort of so strong that they kind of get in the way of actually seeing the thing that we're talking about. And I think, part of what Andy's been saying and part of what we've noticed in our work is that these things are incredibly transformative. When you start to look at, a glass factory or a chemical plant or some of these industrial users, a steel mill, where they need heat and they might need hydrogen and they need a lot of electricity, and you sort of begin to look at the alternatives that you have for those services or those energy sources and the scale that you need. It's just very, very difficult to sort of figure out something else that would do what these things can do. And I go ahead.
No, I didn't mean to interrupt you.
Oh, that was a thumbs up?
No, that was I'd like to speak next.
Okay, yeah, go ahead. Well, I guess I was just encouraging
And
the
then
audience.
I want to take questions. Okay.
I was encouraging the audience to really sort of imagine how much easier the decarbonization problem would be if we had access to a lot of these that were being produced in kind of large factories, making them very cheaply, and we could put them in all the places where we're having a really difficult time decarbonizing.
Okay, so we're this new generation of reactors. We call them small modular reactors, and I just want to give you a little bit of a concept of where this industry's gone. There's 450-ish reactors, commercial reactors, operating in the world today, and almost all of them apply what's to achieve the safety, which is statistically the best industry in the world. We use what we call defense in depth. So we have backups on the backups on the backups on the backups, which means a lot of equipment, which means a lot of people, a lot of maintenance, a lot of procedures. And because of the way they're designed, you need an exclusion zone around these large reactors that's sort of 20 kilometers. Because if in the event of some kind of disaster, that is theoretically possible, but unlikely, you've got the zone that you got to take care of. So these newer technologies are not pressurized. And because they're not pressurized and they use liquid metals and things like that to achieve the safety, and we've proven that you can walk away from them and they shut themselves down, you don't need some of those backups on the backups on the backups. The plant gets simplified, it gets smaller. The lack of pressure means the walls of the vessels are this thick instead of this thick. And so it's simpler, right? And when you look at all these applications and look at the potential demand, you can make them smaller because most of the demand is in that 100 megawatt kind of range, not 1400 like the big ones. So they're simpler. You can manufacture them in factories to control the quality, something Eric mentioned earlier about how a lot of these big nuclear projects go over budget and over schedule. Stick-built construction of a massive nuclear plant with all the regulatory framework, and it's hard to do. So if you can get some of the construction done modularly in a factory under controlled conditions and put it together like Lego at a site, it's a big advantage. So I'm just trying to paint a little bit of a picture of this newer generation of nuclear and how it's different from the old one, and that these perceptions that Eric's talking about, we're working to dispel many of them.
I think that's great. Yeah, because that no longer needing to sort of have really complex engineering to achieve that unparalleled level of safety. That simplicity is very easy to understand, which is great. And you can have a great deal of confidence in it because you can see very clearly that it's going to work and there aren't as many potential points of failure. So for the regulator, that's awesome. But ultimately, that simplicity makes them a lot cheaper, right? And easier to make in a faster amount of time, in a more manufactured environment. So, there's really many advantages. And I can see you may want to add another comment, and please do, but just before you do, please do raise your hand if you'd like to ask a question. We'd love to take some questions from the floor. I can see a couple of hands. Andy, did you want to make a quick comment?
So while the mic's moving, to give you a perception of ARC, I usually use pictures, right? So it's easier picture. I don't have to describe it, but an ARC reactor would fit on about the size of a Costco parking lot, and the buildings themselves would be smaller than the warehouse, just to give you a sense of the size. And that zone you have to look after in the event of a potential disaster is the parking lot. You don't have to go any further. So
whereas the conventional gigawatt scale light water reactor is like building a cathedral inside a cathedral.
correct.
Right. Okay, so please, one question here and then another question here. Do we have microphones? Oh, the microphone's there. Good, thank you.
Hi, I actually have 3 related questions, but they're short, so hopefully I can fit them in. Cost, scalability, and the speed. So mentioned competitive with natural gas. So curious, what we're thinking there in terms of a cost per megawatt hour, looking over a 30-year time horizon. It sounded like that was sort of the age or operating lifespan of these reactors. Scale, we talked large scale, and I'm curious, how small scale these can be sort of brought down to in sort of a decentralized generation scheme. And then ultimately, assuming an accommodative regulatory environment, what are sort of production timelines on a small scale, cost competitive modular reactor?
Me again? Yeah. Okay, we're not going to commit to a cost. So sorry to disappoint you on that one. We are going to say competitive. I've heard over the course of time some of the prices we were throwing around in Alberta, monthly prices of electricity in Alberta, and we can do way better than that. So probably not going to commit, but you know, I'll give you a number because I feel bad not doing that. We're going to be $100 a megawatt hour or less, something like that. If you look at electricity, I don't know what you're looking for, whether it's electricity or heat energy, whatever. We haven't really priced heat energy yet. So scalability, we're talking mostly about ARC and NB power today. There are small modular reactors that can that are designed to work off grid up to about 5 megawatts, if that's of interest to you in this answer. So mines with no distribution systems to them, or northern communities. There are very small modular reactors at sort of 5 megawatts or less, 2 of them being developed in Canada right now in Ontario. New Brunswick Power is not directly involved, but that's the application they're looking for, and they're looking to substitute out diesel generators in these mines or northern communities where you got to take a tanker up through the ice every year to get the fuel supply to people. So that's so cost, scalability, and what was the third one? Regulatory environment. So it's about 11 years from the time you make a decision to the time you go commercial right now with the current regulatory framework. Our sort of vision or target is 5. So I hope that answers your question. Right now, if we have to operate under the current regime, it's about 11 years from the time you make a decision till you get some energy out of them.
So I'm just going to provide a slightly different perspective. I think what you've said, Andy, is correct for the sort of scale that you guys are contemplating deploying these things in the near term. But if you were deploying them in a system such as the one that I showed, your generation cost would be below $30 a megawatt hour. And we've done very extensive cost studies that validate this. So when you create a manufactured product, so when your project has almost no construction left in it, you can, and when you're deploying a number of these things in the same site, and when you have the ability to share the staff across multiple units, you begin to achieve real economies of scale that combine the benefits of modularity with the benefits of large-scale projects. And we believe this will be how large-scale hydrogen is manufactured in the future. And the speed with which these, we're currently in pre-feed studies on 4 of these, and we're looking at rates of deployment in the sort of 10 to 15 gigawatts a year per project. So very large-scale projects. And the marine kind of shipyard manufactured approach that Kirsty was talking about in her talk, it's similar. You can basically, the shipyard is a factory for making ships, and you can assemble other complicated things into those ships, and you can make very low cost power generation units and units that make hydrogen and fuels with that power. So we see that there will be a business model to deploy advanced nuclear that will be gaining real traction in the early 2030s, and that will be very large scale, and it will be the kind of projects that oil and gas companies are used to investing in. They're not used to investing in $1 billion project. They're used to investing in $10 or $20 billion projects. And that's what we've been involved in starting the design of.
Great, thanks. And I see another, do you have another hand here? There's a woman at the front, and, oh, thanks, great. And then this gentleman here next. We take a couple of questions.
Yep. Thank you, I'll be quick. Can you comment on the waste?
For ours.
Technology and...
what would you like to know about the waste?
Just how would you encapsulate them?
I can do a quick comment on the...
Sure. Thank you.
You can follow me up. So because we're a smaller reactor, we're compared to conventional nuclear, we're only producing about 10% of the same spent fuel. in terms of volume. So there's less of it, first of all. Second of all, because of the technology we're using, fast spectrum, we're not producing the same type of high-level waste with, half-lives of, on the scale of hundreds of thousands of years, 300,000 years. It's more like on the scale of hundreds of years. So it's not as bad, there's not as much of it, and also our technology, our reactor can recycle the first core to put in another core. And we can keep recycling that fuel to get 99% of the energy out of the uranium that we mine. As long as we can keep recycling it, we need recycling to be an activity in Canada that is acceptable and to the public, to the regulator, and economical. But we have studied with, the UK has done studies on, we have sodium bonded metallic fuel, and that has been deemed in several studies to be technically sound to bury it in the same way we would be burying the CANDU fuel.
I think that's part of the answer to your question is that the nuclear industry today, the plan for the radioactive waste is to bury it deep in the ground, right? Deep geological repository. So you're always going to need a deep geological repository. It just might be 10 times or, some multiple of that smaller because we can keep recycling the waste. And in fact, New Brunswick is working with another technology, Moltex, which takes the spent fuel as its fuel. So we're reducing the waste. So hopefully we've answered your question.
Yes, Billy Rideout with Exergy here, and I'm sold, and I didn't have to come to this panel to be sold on this. If we're committed to net zero, we need to think seriously about this. But I don't see leadership sticking their neck out federally or provincially and waving the nuclear flag. It's just political, not going to work for them, not going to get them in office. And, I kind of reflect on during the playoffs last year, the Canadian Association of Dairy Farmers decided to go net zero. And I think it was around the playoffs. And I'd never seen so many cows on TV. Like it was like every 15 minutes there was dairy farmers going net zero. So my question is, where is the marketing campaign? Because it seems like it's awesome, the walls are thinner, and not just, I'm not talking maybe as a consortia of nuclear, not as an individual technology. It just seems like the awareness is not there.
Yeah, so I keep hogging the mic here, but in Canada, most of the nuclear operating to date's been done by crown corporations who are sort of, at least in our case, we're banned from marketing, so we're just not good at it. And I think now that there's new technology developers like ARC, and there's a couple others in Canada that are developing technology as well, we have to figure out how to do it. We do have a lobby organization, the Canadian Nuclear Association, which is starting to look at, what do we have to do? The nuclear industry talks to the nuclear industry. So I'm happy to get out here and talk to a different industry because it's that open-minded change mentality again. But we suck at marketing, and we're going to have to figure it out. So we don't have a plan yet, Bill.
I think it's a very interesting question, and there are a lot of layers to the question. But one of the things that we've found as we've engaged more broadly internationally as well around the role that nuclear could play in de-risking net zero is that right now, in part because of what you just said, Andy, nuclear exists in a kind of a weird bubble. So people, if you ask people about nuclear, the first thing they're going to bring up is waste. And everyone thinks that's the smart thing to ask about. And we all think that there must be some really risky thing that's related to waste. And then the next thing people ask is about cost. And we sort of, the marketing campaign around nuclear has been 100% by the opposition. So they've created a kind of a context or way of seeing nuclear that's really all about the drawbacks of nuclear. And I'm not complaining about that or whining, but I'm just saying that what we found that's really interesting that's starting to happen now is that applications for nuclear that are really quite meaningful and useful are starting to enter the public consciousness. And for the first time, people are have something on the positive side to balance the negatives. Now, we all know that you can die by getting into a car or that you can die by getting on a plane, but we do that all the time because the positives of getting in a car and going on a plane, we consider that to be worthwhile, right? And in a way, the biggest myth about nuclear is that we don't need it. And once people begin to see that it's really useful, it can really help us survive on planet Earth with the climate change challenge, or that it could repower a coal plant in our community and we could all keep our jobs in that town, or it could allow us to keep our chemical industry operating here and a whole bunch of other really interesting, important benefits. Once we see that, once people start to see that, they really think about those risks in a different way than in this kind of weird sort of box where you only think about the negative stuff. And we see that trend growing very, very rapidly around the world today. The three drivers that you mentioned, energy security and climate and economics, those are not abstract sort of, goods. Those are things that really affect people's lives and their sense of security and their ability to live well. And I think we're increasingly seeing from the countries that do have a lot of nuclear in Europe, for example, it's really beneficial for those countries that they have those plants. And so I think this will change we still need the marketing campaign, but I think as this enters the public consciousness and we begin to think about this as positives and things to worry about, I think people will make practical, good decisions and we'll see a lot more support for nuclear.
Yeah,
Let's do one more at least. This gentleman's been trying to ask a question.
We are out of time, so if I can get a nod from the organizers that I can go over a few more minutes. Oh, thanks. Great. Please. Oh, there's a mic coming to you.
What level of enrichment do you need for this reactor system?
It's nominally about 13% enrichment. But the benefit is it lasts a really long time. And it's sitting in a, strong wording, but proliferation proof vat below ground. So it's protected and it's 20 years worth of 100 megawatt electricity.
Fantastic. Well, that's a great way to end. So I think, what we're seeing is certainly, I think the trend that Eric is pointing to is this incredible demand growing around the world for nuclear technologies to come to market and start meeting this whole range of different needs around power and heat and hydrogen. And so we would, really happy that these technologies, these products are being developed and coming to market, and we wish you well and every success. And, thank you to, your courage and leadership, Andy, as a customer that's prepared to actually, step out and start, ordering these things. So I think this has been a wonderful discussion, and I would love you to please join me in thanking our great panel.